Let's check again.
Can you hear me now? No. Yes? Okay, good. Hi, everyone. Thank you for being here. Today I will talk about our work with Leo Lampropoulos and Benjamin Pierce. And in particular, I will talk about how we automatically generate good random data generators for data that satisfy inductive relations. And in the process, I will explain. And is this better? Okay. And in the process, I will explain what we describe as a good generator. These generators are used for testing in QuickCheck, which is a property-based random testing tool for Coq, and as you might have guessed, a port of QuickCheck, which is a famous random testing framework for Haskell, and it has been ported in many languages and also proof assistants. So in QuickCheck, just as in QuickCheck, we can test properties for counterexamples by randomly generating inputs. So in particular, to test the conjecture of the form for all x's of type A, then P of x is true, first we need a generator of random inputs, which is a program of type GA that will generate input for us. Then what QuickCheck will do for us is to test if P of A is true. If it's not true, then we have discovered a counterexample, and we will go ahead and fix the bugs in our definitions. Otherwise, we have gained more confidence that that our property is true, is valid, and we will repeat the process unless we are confident enough that our conjecture is true. However, the most interesting properties that we need to test are conditional. And that means that the inputs are guarded by some preconditions, and that before we are able to test the conclusion, we should first check if the precondition is true for the generated test cases. So we will, again, generate some random inputs, and we will first test if Q of A is true. If it's not, then we will have to throw away the test case. Otherwise, we will, again, test the conclusion, and if it doesn't hold, then we found the counterexample. Otherwise, we repeat the whole process. However, this can be very, very problematic when the preconditions are sparse. So it could be the case that the precondition holds for a very, very small portion of the range of our generator. And we can see an example, an instance of that. Say that we want to prove preservation for simply typed lambda calculus. And the naive approach, and first we want to test that to see if it's true. And the naive approach would be to generate to write some random data generators for terms, and then have a type inference function to infer their type, write the step relation as a function to see what is the result of evaluating this term, and then check if the resulting term has the same type. However, if we use QuickCheck to test that, QuickCheck will complain that most of the test cases were discarded, and the property has found to be true, to be valid, only for 23 test cases, which does not give us much confidence for the validity of our property. And in fact, out of the many terms that were generated, most of them are discarded, which is not very satisfying. So what do we need to test this kind of conjectures? And we need a good generator. A good generator is a generator that generates inputs that satisfy Q by default. Then we don't have to test if Q is true for the generated inputs, and we can just go ahead and test if the conclusion is true. However, this can again be problematic. Imagine this situation where several where the output of the generator is a very, very small portion of the elements that satisfy Q. And it could be that counterexamples lie outside the range of the generator. So to claim that the generator is good for a conjecture of this form, we need two properties. First, we need the generator to be sound, meaning that for every element in the range of the generator, Q must be true. And in addition, we need the generator to be complete in the sense that every element that satisfies Q should be in the range of the generator. And in the previous example, we are interested in writing a generator, namely GenTerm, that's parameterized by the typing environment and the type, and it generates terms such that the terms are well typed in this environment by this type, and also every term that is typed in this environment by this type is in the range of the generator. However, it turns out that doing this can be very complicated, and this is the generator for our very small language that has 2 types and 4 type constructors, and if we extend the language a bit, this can be the topic of a research paper. So what we have achieved in this paper is to compile inductive relations to generators that generate elements that satisfy this relation, and prove that our generators are sound and complete with respect to this relation. Back to our example, we can generate a, given the inductive relation has type, we will automatically obtain a generator that generates only well-typed terms, and it can potentially generate all well-typed terms. And I will give you a small hint of how these generators look like. So the idea is that for each constructor of the relation, we will generate a subgenerator that satisfies this relation via this constructor. In this example, I will show you how we can obtain the generator for the abstraction case. The abstraction case tells us that an abstraction is typed by a term T1 arrow T2 if in the extended environment that body is typed by type T2. So we look at the conclusion and we see that in order to, the type of an abstraction is arrow T1, T2, so our subgenerator will start by pattern matching the first input to see if it's an arrow or not. If it's not an arrow, then this cannot be, this inductive relation cannot be satisfied via this constructor, so we return none. Otherwise, if the type is T1 arrow T2, then we will look at the conclusion again, and we'll see that the term must be an abstraction, so we will return an abstraction. And what's left to do is to instantiate the body of the abstraction here. And we can do that by a recursive call to the generator we are building. And this will give us a term that's well-typed. So we can go ahead and use the automatically derived generator to find counterexamples. And indeed, QuickCheck will give us a counterexample, and we will use this information to hopefully fix the bugs in our definitions. So I claim that we are generating provably good generators. And in fact, it turns out that we can use exactly the same machinery we use to obtain the generators to obtain their proofs of correctness. In particular, when we instantiate our algorithm with generator combinators, we obtain the generator terms. But if we instantiate good generators, if we instantiate our algorithm with the corresponding correctness lemma, we will obtain their proofs of possibilistic correctness. We have evaluated our approach, and we tried to answer several questions, including is the class of inductive definitions we're able to handle large, general, and useful enough. And if the generators we're automatically producing are efficient, and also if we achieve a good coverage and distribution of test cases. So first, we evaluated our approach by automatically testing specifications found in the software foundations textbook. And we found out that 83 of suitable for testing theorems could be tested with our approach. And what I mean by suitable for testing is that we discarded some of the test cases, some of the specifications as too easy. For instance, unit tests, which are uninteresting from a generation perspective. And some other ones were too hard for generation because they involve, for instance, generating high-order properties. And some instances of relations that we cannot handle is for generate relations that involve functions or existentials. We have also evaluated the performance of our approach, and we have compared our automatically derived generators to handwritten ones that were used in an information flow controlled case study, where the goal was to generate indistinguishable machine configurations. We found out that our generators were 1.75x slower than the handwritten ones, but they had the same bug-finding performance, and we were able to tweak the distribution of the automatically derived generators in order to achieve the same bug-finding performance, meaning that the counterexamples that were found per second. And in conclusion, I show you our approach in generating sound and complete generators for inductive relations for free. And in the future, we would like to extend the class of inductive definitions we can handle. And we would also like to use the same machinery, not only to derive generators, but also to derive decision procedures to test the conclusions of the conjectures we would like to test, and we want the corresponding proof of correctness by using the exact same machinery. And lastly, we would like to derive shrinkers, which are programs that shrink counterexamples, but we would like to do it in a way that the inductive relations are preserved. You can find a QuickCheck on GitHub, and you are welcome to try it and tell us what you think. And that was all for today. It might have been a bit fast.
We have enough time for ample questions. Any questions?
So I have two questions. First of all, I did not understand your evaluation. If you were running your generator on examples from software foundations, which includes only theorems that actually were proved, where were you finding counterexamples? Maybe I missed something there.
I didn't hear the question very well.
Say again, please.
Can you repeat the question?
Can you repeat the question? A bit louder, maybe.
So if you run your counterexample checker on the examples from software foundations, you shouldn't find any counterexamples.
That's true. In this experiment, we were interested in being able to automatically test the specifications rather than finding counterexamples to see if we could derive the checkers automatically that test these specifications. And for the counterexamples, to evaluate the counterexample finding performance, we performed the second case study.
Oh, maybe we can take that offline. Second question.
So it was a different case study.
It was a different case study?
That we used to measure counterexamples.
Okay, thank you. Second question, do you get any insights from this, or do you have any tools for biasing the generator to work on edge cases and corner cases rather than the routine cases?
So there are two things. So first, we prove that every case can be generated by proving completeness for the generator, but so we also want to have a good distribution, and this is not guaranteed by our reasoning, because we only reason possibilistically, but we have a way that you can annotate the inductive relation so that you can tweak the distribution of the generated test cases.
Thank you.
So, thank you for your talk. You mentioned needing to manually tweak the generators a little bit, which I understand, of course, is necessary. But could you elaborate a little bit on what sort of tweaks?
We didn't manually tweak the generator. It's exactly the same thing. We can add annotations to the inductive relations so that we can tweak the distributions of them. We can fine-tune the weights used in the generators.
Okay, thank you.
Can you explain a bit more what classes of inductive relations this empirically works for?
So yes, I can. A slide would have been helpful, but yes. The shape of the inductive relations, we can handle inductive relations of arbitrariety, and the types of the arguments of the relation is just a simple inductive type. And then its constructor universally quantifies over some variables, again, of simple inductive type. We have some preconditions, and which are inductive relations applied, of the same form applied to some expressions. The expressions at this time consist only of variables and constructors, and then we have the conclusion, which is the inductive relation being defined. Is this helpful?
The function induction package of COP generates inductive relations from function definitions. So you start from a recursively defined function, you obtain an inductive relation. Did you try to apply your tool on this kind of inductive relations?
I cannot hear you very well.
Can you speak closer to the mic?
The function induction package of COP generates inductive relations from recursive definitions of functions.
Mm-hmm.
Did you try your package on this kind of inductive relations?
No.
Might be a good idea.
No, but this sounds interesting, so we can discuss about that afterwards.
How do you specify which parts of the arguments to the relations are inputs and outputs?
So when the user can type a command to automatically derive a generator, and it's part of the user can type derive a generator for this relation, and when they write the relation, it's clear which arguments are inputs and which are outputs.
Do you support multiple outputs?
Right now, no, but the algorithm can be generalized. Yes, we can. As of yesterday, we can.
Sorry, thanks for the great talk. Maybe I missed this. Did you say how long it takes to generate the generators?
Oh, not that long. The proofs are usually, the proofs take longer, but most of the time is spent on type checking them.
And,
so the terms are generated quite fast. The proofs might take a while to type check.
Do you have any intuition for how that scales with the size of the relation? Or the number of constructors in the relation?
No, because we had like very reasonable times when we in every of our case studies. So
Thank you.
Any more questions? Let's thank the speaker again.
you.